second episode of our webinar series, Simulation Fridays. My name is Paschalis, Dompoudis, and I will be your presenter today. So I'm an application engineer here at Simtec. My main focus is supporting the Ansys Optics and Photonics portfolio of tools. Today's topic is smarter electro-optic infrared sensor design with Ansys Optics. So we'll be exploring how simulation can significantly improve the development process for these complex systems. So with that in mind, let's get started. To begin, let's quickly cover some basic concepts of what electro-optic infrared sensing is and the challenges involved in designing these systems. Electro-optic infrared are systems that essentially act as our eyes in the infrared spectrum. So they combine optics and electronics to detect the heat signatures emitted by objects, allowing us to see, track, and identify these objects. They generally consist of three main components: an infrared detector, which captures the infrared radiation, a focusing lens to direct that radiation onto the detector, and finally a display or imaging device to show the resulting image or data. However, designing these systems can be complex, so engineers need to validate the performance of the optical components and ensure the system operates reliably under different conditions. So more importantly, they must account for complex multiphysics interactions. For example, how changes in temperature can affect the lenses and cause distortions, or how the airflow over a sensor on a moving vehicle, what we call aero-optical effects, can degrade the image quality. So ultimately, the goal is to analyze all these factors and optimize the final system design. So, on this slide, we have an overview of the multiphysics workflow we will discuss today. So the goal of this example is to see how a scene heats up when exposed to the sun, and then to simulate what an infrared sensor would actually capture from that scene as its temperature changes over time. So the process has four main steps. In step one, we begin in Ansys Speos. We simulate the solar radiation hitting the scene to calculate a heat load. In step two, that heat load is passed to Ansys Mechanical. Mechanical performs a transient thermal analysis to determine how the temperature of the scene changes over time. In step three, we return to Speos. We take the temperature results from Mechanical and use them to model the infrared energy being radiated by the hot objects. We then set up our virtual infrared sensor to see, in quotes, this infrared radiation. And finally, in step four, we automate this entire loop using Ansys System Coupling, which manages the data exchange between the thermal and optical simulations. So the final result is the time-varying infrared signal as captured by our sensor. So we begin with the first phase, the solar irradiance simulation. The main goal here is to accurately calculate how much energy from the sun is absorbed from our scene. So this result will be the primary input for our thermal analysis. So this step, as mentioned previously, is performed in Ansys Speos. To begin, we set up a realistic sun and sky model. For this, we use a Speos ambient source called US Standard Atmosphere 1976, which provides a physically accurate spectrum of sunlight. Next, as you can see in the image on the left, we place a 3D radiance sensor over the entire scene. And the purpose of this sensor is to measure the total solar power landing on every point of our model's surface. And once the setup is complete, we run a direct simulation in Speos, and the result is what you see on the right, which is a color map showing the distribution of the solar heat load across the scene, which is measured in watts per square meter. And finally, we export this irradiance map as a text file. Moving on to the second phase, we take the heat load data we generated and bring it into Ansys Mechanical to perform the thermal analysis. So the goal here is to simulate how the scene's temperature actually changes over a period of 1 hour as it absorbs the sun's energy. So first we import the solar heat load from the text file we created in the previous step. And for that, we use the external data component in Ansys Workbench, which maps the heat values onto our 3D model. And the image on the top right shows the imported heat load applied to the scene in Ansys Mechanical. So next we set up the thermal simulation. This involves meshing the geometry, applying boundary conditions, contact regions, and finally, and most importantly, defining a system coupling region. So this region is the interface that allows Mechanical to communicate and exchange data with SPEOs in our coupled workflow. So with the setup complete, we run a transient thermal analysis. The simulation calculates the temperature distribution across the entire scene over a total duration of 3,600 seconds or 1 hour. So the result as seen in the animation is a dynamic temperature map. What's important to notice here is that the road heats up much faster than the vehicle. So this temperature difference between the objects in the scene will be important for the final infrared signal. For phase 3, we go back in Ansys SPEOs to set up the optical side of the simulation. So here we want to create a virtual infrared sensor and simulate the thermal radiation from our scene using the temperature data we calculated in Mechanical. So first we define every object in the scene as a thermic source, as you can see here. So this tells SPEOs that these objects will radiate in the infrared spectrum based on their temperature. The amount of heat they radiate is controlled by the transient temperature field file that we get from Mechanical. So then we set up our camera sensor and we run an inverse simulation this time. So finally, the image on the right shows a baseline result just for comparison. So this is what the sensor would see if every single object in the scene was at a uniform temperature of 22 degrees Celsius. So as you can expect, there is very little contrast. It's almost like a totally gray image because there are no temperature differences. Now, the final step is the co-simulation, where we use Ansys system coupling to connect our thermal and optical analysis. The role of system coupling is to act as a coordinator and orchestrator. It synchronizes Ansys Mechanical and Ansys SPEOs, allowing the temperature data to be transferred from the thermal simulation over to the optical one as the solution progresses. So the setup process, which we can see in the screenshots, is very straightforward. So first we add both Mechanical and SPEOs as participant in Ansys system coupling. Next, we define the interface that connects them. And this interface is the coupling region that we defined earlier in the Mechanical setup. We then specify exactly what data to transfer. So we tell system coupling to take the temperature result calculated by Mechanical and use it to update the temperature of the thermic sources inside SPEOs. And finally, we set the simulation time and the time step. So when we start the simulation, system coupling automates the entire loop. So at each time step, Mechanical calculates the new temperature. System coupling passes that result to SPEOs, and SPEOs generates the updated infrared image. And this process repeats until the full simulation time is complete. So after running the full co-simulation, we can look at our final results. So on the left, you can see the full transient response as an animation. The left animation is the temperature map from Mechanical. The right one is the resulting infrared image from SPEOs. So you can notice how the road heats up and appears progressively brighter to the sensor, while the vehicle heats more slowly, which creates a distinct shape. So the graph on the right is where we quantify this observation. It is a plot of the contrast between the vehicle and the road over time. So you can see that both metrics increase as the simulation runs, and then they begin to level off as the scene approaches a stable temperature. Now, the workflow we just saw was pretty much very simplified. its real power is how it can be extended with advanced features for higher realism. So we'll now briefly introduce 4 key extensions to this workflow we saw before. First is upgrading the camera model with realistic optical performance data. Second is improving the environmental source for a more accurate thermal analysis. Third is performing a sensor level simulation, and finally running a full multiphysics analysis on the optical components to predict deformations. So our first extension is upgrading the camera model. So the initial simulation used a very basic model, as you can see in the table at the top left, the version 1 distortion file. This model only captures simple distortion. To improve this, we can use a reduced order model that is generated from a lens design in Ansys Optics Studio. This ROM will be far more realistic, and it can capture critical effects like geometric and chromatic aberrations, among other things. The main advantage also of the reduced order models is speed without sacrificing accuracy. So as the image on the top right shows, a simulation using the full geometry of the lenses inside Speos takes 30 minutes. The ROM achieves the same highly accurate result in just 6 seconds. Our next enhancement could be the modeling of atmospheric effects, which we can do in 2 key ways. First, we can improve the environmental source that we used. So here, instead of using this default source available in Speos, we can use Motran, which is a third-party tool that can couple with Speos. So we can use a Motran source in order to get a highly accurate model of the sun and the sky. And this provides a more precise solar heat load, leading to more accurate temperature predictions in our thermal analysis. The second way, we can simulate the optical path to the sensor. So while our first simulation assumed a clear path, only air between the sensor and the scene, we can add real-world impairments. We can use gradient index materials to model distortion from turbulence. Or we can use mice scattering to simulate how particles like haze or fog would reduce image contrast. Another key enhancement is running a multiphysics analysis on the optical components, which is often called the STOP analysis. This stands for structural, thermal, and optical performance. It predicts how physical forces and temperature changes deform the lenses of the optical component, which finally degrades the image quality. And you can see a comparison, some comparison images at the bottom right. For airborne systems, we can also add aero-optical effects. So for that, we use Ansys Fluent to simulate how high-speed airflow creates density variations that eventually distort the wavefront passing through to the sensor. Our final enhancement is sensor level simulation, where we simulate the entire camera system, including electronics and software, not just the optics. So the process is managed by a tool called Speos Sensor System Exporter, which starts with the ideal optical image, which is essentially an irradiance map on the sensor's surface. First, it creates a raw image by applying a sensor model based on the EMVA 1288 standard. So this adds real-world imperfections like electronic noise and non-uniformity. And for even higher accuracy, fidelity, we can use Ansys numerical to calculate also the spatially and angle-dependent quantum efficiency of the sensor. And second, this tool, the Sensor System Exporter, simulates also the camera's internal image signal processor. So this applies algorithms for demosyncing and color correction to create the final developed image. So this workflow is essential for accurately predicting final image quality and testing different sensors virtually before building the physical prototype. So that concludes our presentation. Thank you for your time and attention. As a reminder to stay within our time, there is no live Q&A. Please feel free to email me directly with any questions you may have. Simulation Fridays will also continue on Friday, October 17th, with a topic on reducing noise and vibration in electric motors. Thank you again for joining and have a great day.